Okay, so the next thing to talk about is single slit diffraction. This is a case where light goes through not one slit, or not two slits, but just one. This distance, the slit width, I represent as a distance A. Some books might do capital D, so I don't know. I think you're using the same book I did. And it puts an image on a wall that looks kind of strange. You've got a big bright spot in the middle, and then you got some fainter spots that go outward from there. So this will be the middle spot, and then this will be dark number 1, dark number 2, dark number 3, and so on. The phenomenon and how it works, every time I read it, I understand it, and I have that moment of clarity for about 20 minutes, and then I lose it. The equation ends up being very similar to the one that we just did for double slit. Except the key difference is this one predicts dark fringes. And why do I say it's key? Because we did this before, right? An integer number of wavelengths should give us bright spots. This equation gives us dark ones. Read the book and figure it out. I think it has to do with the fact that the edges are 1/2 of the distance up from the middle axis, but I don't know. It has something to do with the the assumption. Okay, for clarity, because this looks really similar to the other one, I tend to use a capital M here to represent where this dark fringe is located. Okay, so I think the book actually might use M or N. I use a capital one, and the reason it's bigger, it will become clear a little bit later on. As far as this equation goes, look, it works exactly the same as everything else that we've done. So if, say, I measured this central maximum to be, I don't know, let's say, 20 centimeters, and we wanted to know, I don't know, given, let's say we have some kind of very red wavelength laser, and we shine it through all this stuff, and we use the same data that we had before. Let's say this is 10 meters away. Maybe find how wide is the slit based on this diffraction pattern that we get. Okay, so we would say A sine theta equals m lambda. A question I'll ask you, what is m? We're measuring the central spot in theory, right? So if that's the case, this distance, that goes to the first dark spot. That's how we define the central maximum, right? From where it's dark to where it's dark. And then the middle axis is in between. So this m is really 1 in this problem that corresponds to that location. Okay, I see 20 centimeters are really 10, because all these measurements are measured from the middle axis to that location. So that's really, truly 10 centimeters. Compared to 1 meter, that's a factor of 100. This is probably a small angle. So let's say A tan theta. And if that's true, that's A, I guess, 10 over 1,000. With the 2 centimeters, it canceled out. No, that's not A. That's A. Okay, so I think we want to define A. So let's use these two parts. Lambda equals A, looks like, 10 over 1,000. So A is 10 over 1,000, that's 1 over 100. That equals 100 lambda, or 100 times 600 nanometers. Pretty big. What's that? Yeah, 60,000 nanometers, or I guess 60 micrometers. So that's how to do a problem like that. What we notice when we do a real double slit interference experiment, if this is one slit, and let's say it has a value of A, you'll see a pattern that kind of looks like this. Right, where this is the central bright spot, this is the middle of the pattern, and this might be capital M is 1, capital M is 2, etc. For the interference pattern, we expect to see dots. And in real life, we see something that looks like this. This will be 2 slit of D. And what do we say? In real life, we see a pattern that looks like that. And something I think I posed in the interference video is, where are the dead zones coming from? Well, look, if this is a real diffraction pattern, or real interference pattern, the interaction of slit 1 and slit 2 produces this pattern. But look at the 2 slits. They've got some kind of width, right? So each one is casting a diffraction pattern. So in a way, it's taking this 2 slit interference pattern and wrapping it up inside these little things that I'm going to call envelopes. Well, this one, yeah, one side says that you should have a max there, but the other side is multiplying it by 0. So the net effect is we've got these dead zones in between the envelopes that are loaded with smaller interference fringes here on the inside. In the lab, I think we had, oh, what was the pattern? I think D was 0. Which one was it? I think it was 0.25 millimeters is the one I said was good. And each of them had a slit width of 0.04. And here's a good real question to ask. How many interference fringes would there be inside the central envelope? Or how many little spots are you going to find inside this first kind of big blob of spots? What's the key assumption that we would make in that problem? Here on the screen, what are we noticing? There is some location. This is where the dark spot happens, right? And that's capital M equals 1. What's something that we should say? It's the same laser, so you have the same lambda or same wavelength going through these 2 slits. So a good question would be, what is the little m number at that exact same location? If we find this, we can maybe use that information to kind of backtrack and figure out, well, what order number is that fringe, and then is it visible, right? So let's do that. We'll set about trying to solve these 2 equations, d sine theta equals m lambda, and a sine theta equals big M lambda. And we have to simultaneously solve them. What's another assumption that's true about this? We're trying to solve for little m, but this location is the same in both formulas, right? I mean, it's the same laser, so lambda is going to be a constant. And then what about this position? That's also going to be the same thing, right? It doesn't make sense to be talking about, oh, at this one spot, this one's here, but the other one's up there. No, it's not. It's the same spot. So I would say try to collect the constants on one side and the variables on the other. So let's say we did d over m equals, I guess, lambda over sine. And in this case, we have a over big M equals lambda over sine. And if these are all equal, then that connects these 2. d over m equals a over big M. Okay. So our goal was what? I think it was little m. Rearrange this with some cross multiplication. And I think we're ready to go. What was big M? If we're talking about the central envelope, this one, then it terminates at big M equals 1. That's the dividing line between the center and the next envelope. So that'll be just 1. D in this experiment was at 0.25 millimeters. And the slit width of each one is 0.04. And I may not be able to really do that without a calculator. I'll try. 4, 8, 12, 16, 20, 24. I know M is 6, so 24, and then 1 over 0.04. There's 1 left. That looks like a quarter. Is this our final answer? when we look at the central maximum, what are we saying? The envelope ends here at 6.25. Do you see a fringe there? No, you don't. But you do see 6 is safely inside it. And so it's 5, 4, 3, 2, and 1. Is that how many fringes we have? 6? What about the other side? Okay, 7, 8, 9, 10, 11, 12. Is that all? Don't forget about 0 in the very center. There are 13 fringes visible in the central envelope using these 2 sets in the lab. So that's a fun problem. Here's one that you should do on your own. How many fringes are in the second envelope? We already know that this is big M equals 1, and this is big M equals 2. I would challenge you. Count the number that you would find inside here. I don't know it off the top of my head.